we're going to continue with sequences and summation notation. This again is section 8.1, and we're going to be looking at summation notation. Summation notation indicates that we're going to be summing the first n terms of a sequence. So the sum of the first n terms of a sequence is represented by this summation notation. So if we want to sum the first n terms, starting with 1 up to n, this is called your lower limit and your upper limit. We'll talk about the I in a minute. Okay, of a subscript, that should be a subscript I. That's a typo. Right here, where the expansion of this notation means that I is going to start with 1 and it's going to proceed to n. So taking turns letting a subscript I be a subscript 1. The next integer after 1 is 2. So we have a plus sign because that means we're summing. That's what the summation notation means. Plus a subscript 2 plus a subscript 3 plus ... plus a subscript. When we get to the upper limit of summation n, we end there. I is called the index of summation. N is called the upper limit of summation, and 1 is the lower limit of summation. This symbol is the capital Greek letter sigma, and it stands for summing the first n terms of a sequence. Any letter can be used for the index of summation. The index of summation up here was I, lowercase I. It's common practice to either use I, J, or K. So any letter can be used, but common practice is I, J, or K. And the lower limit does not have to be 1. If I didn't want to add the first term of a sequence, I could let I equal 2 to n, which means I wouldn't have the first term. This term would not be here. Okay, so let's see how summation notation is used over here. Okay, we're asked to expand summation notation, and that means write out the sum and evaluate. So there are 6 examples present right here. I don't want to start with example 1 because it's a special case, and sometimes we don't get the full impact of what we're supposed to be doing when we look at a special case. So actually we'll probably end up doing that as one of the last problems. So I'm going to go out of order. I'm going to start with C. Okay, so this is the sigma notation, the summation of the first 6 terms of a sequence, because I see I'm looking at I starts with 1 and it goes up to 6. And because I is our index of summation, we use an I here. If we chose to use J or K, then that would have to correspondingly be either J or K here. Looks like, no, not all of them are I's. Okay, it says to expand. So we're going to expand and find the sum. So if I is 1, we put 1 in here. So we get 2 times 1 squared plus, because that's what sigma means. Now I can be 2, so now let this I be 2 plus 2 times 2 squared plus, now I is 3, so 2 times quantity 3 squared plus, and you go all the way up to 6. So 4 is next, and then 5, and finally 6. And we end there. So I'm going to put an equals here. So now you can either just do this all on your calculator, or term by term you can go back and simplify. So this right here is just 2 plus, and don't forget that you have to do the power first. You don't multiply 2 into this 2. You've got to do the power first and then lastly multiply by 2. So this would be 4 times 2, so that's 8 plus 3 squared is 9. 9 times 2 is 18. It would be good to use your calculator for each of these terms showing the expanded sum. 16 times 2 is 32. 25 times 2 is 50. And then 36 times 2 is 72. Then I'd pick up my calculator and do all that summing on there. So 182. So again, the lower limit was 1, the upper limit was 6. So we take turns plugging into I over here, the integers 1 through 6, and then adding. Okay, the next one I'm going to do is E. I'll do this, and do this. Okay, now notice that your index of summation is not I, it's K. That's okay. It's just a different choice of variables here. And notice that your lower limit does not have to be 1, as mentioned before. So what we're doing here is we're adding the terms, the third term, the fourth term, up to the fifth term. So we're actually only adding 3 terms here, starting with the third term. So I'm going to put equals here, and it looks like I'm going to have to come down here. So first let k be 3. So 2 cubed, and then I've got the minus 3 here. And then plus. Now k is 4, so 2 to the 4th minus 3 plus, and I can stop when I get up to k being 5. 2 to the 5th minus 3. And then equals. So let's just do all this work right here. So that's 8 minus 3 is 5, plus 16 minus 3 is 13, plus, I know that's 32 minus 3 is 29. But of course, use your calculator to help you. And I think that sum is 47. So we're expanding, finding the sum. Next one we'll go to is F. All right, we see a return to I. Who cares if it's I, J, or K? We don't want to add the first term. We want to add the second, the third, and then up to the fourth term. So I think I'm just going to expand it down here. So negative 1/3. I is the exponent, so that's a square, plus negative 1/3 cubed plus negative 1/3 to the 4th. Now, if you went to your calculator, then of course you're going to get a lot of ugly decimals, but before we get to the calculator, let's just go ahead and do these powers on these fractions by hand. So squaring this fraction means square the top number and square the bottom number. You can think about that negative being on top with the 1, so you're going to get 1 over 9 plus cubing a negative 1 is actually a negative 1, and then 3 cubed is 27, plus negative 1 to the 4th is a return to a positive 1, and then 3 to the 4th power is 81. So when you take a fraction to a power, remember that that power applies to the numerator number and the denominator number. Now at this point, I probably would go to my calculator, unless you wanted to get a common denominator, which you could do, but you're going to have a calculator. So if you were to get a common denominator and add all those fractions, you'd get this value. But if you went straight to a calculator, you would get this decimal value. And we're going to round to 3 places. Okay, the decimal answer is just fine. Let's go to D. All right, I'm going to add the first 4 terms of this sequence. Okay, it looks like we got a product. We got K in 2 spots here, so this is going to be a little tedious. So if K is 1, I'm going to have 2 parentheses, 1 minus 3 times 1 plus 2. And then I'm ready to plug in 2 for K. Plus, I'm going to have to come down here. Now K is 3. And then finally K is 4. Okay, so let's come back here to this first term right here. Do each individual parenthesis. So 1 minus 3 is negative 2, and 1 plus 2 is 3. So negative 2 times 3 is negative 6, plus, ready to tackle this term. So 2 minus 3 is negative 1. This sum is 4, so negative 1 times 4 is negative 4, etc. 3 minus 3 is 0, so that's nice. I don't even care what this is, because 0 times whatever that is still 0. 4 minus 3 is 1. 1 times this sum is 6. 1 times 6 is 6. I can see that these are opposites collecting to 0, so finally my answer is just going to be a negative 4. Now I'm going to get back to that special case, part A. Okay, noticing in part A that we're going to add the first 5 terms of the sequence whose general term is 4. Notice there's no I, J, or K here. And it's not a typo. Okay, what this means when you expand is that you don't have any place to plug in the integers from 1 to 5 because there is no J here. So when J is 1, I just still have 4. When j is 2, there's no place to plug in 2, I have another 4. When j is 3, that means just add a third 4. So there's 5 4s that you're adding. So remember, this is 1, 2, 3, 4, 5. This is the first 5 terms of this sequence. So you can just actually multiply 5 times 4, and your final answer is 20. Okay, looking at B, it's kind of another special case as well. J is the index of summation, but there is no J over here to plug in the numbers 3, 4, and 5 for any J. So just like part A, when J is 3, I still just have 4. When J is 4, I just still have a 4. And when J is 5, I have just one more 4. So here this sum is 12. Because I'm only adding 3 4s together. And that's why I wanted to save those for last, because it was kind of a weird one. I didn't want to start with those. All right, so that's that objective. So let's just do the opposite of what we just did, meaning given an expanded notation, expanded sum, let's go ahead and condense it into the notation that we saw up here in the problems. Okay, and I might just suggest turn the video off, attempt some of these on your own, and then come back and see how you did. Just kind of do some self-assessing. All right, we're looking for patterns and structure. It tells us to write the following sums in summation notation. Use I as the index of summation and 1 as the lower limit. So every first term here is going to be term number 1. So all of these need a sigma notation. At least get that out of the way. Okay, and sometimes you'll see the notation like falling below the sigma notation, like I equals 1, instead of out to the side like it was previous. It doesn't matter. So what's left for us to find? Well, we have to find where does the sum end? How many terms are we adding together? So we need a number on top of the sigma, here, 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 etc. And the other thing that we need is the formula that generates each of these terms. So I look for what changes and what stays the same, because I is what changes. So when I look at these terms that I'm adding, I notice that the exponents are all 2. That doesn't change. But I notice that the base of these exponentials right here are changing. So that's going to become your I. I notice also that I'm adding 9 terms. So my upper limit is going to be 9. My formula is I. I is going to be the base, but the 2 stays the same. So this is a summation notation, I equals 1 to 9 of I squared. And if you're not sure about your guess, then just generate a few, expand like we did in the previous problems. Like let I be 1. If I is 1, yes, I get 1 squared. Next, I would have to be 2. 2 squared, yep, that's present. 3 squared, etc. Up till you get to 9, and 9 squared is present here in the sum. All right, so let's try B. Looks like I'm adding 11 terms, so I'm going to put 11 up here as my upper limit. Okay, the exponent's not changing. That's a cube, but the base of that exponential term is, so I would let that be I cubed. Again, you could test by expanding to make sure that your formula is correct that generates those terms. Okay, look at C. I notice that this exponent that's not showing is a 1. The exponents are now changing, but the bases are staying the same. It looks like the exponents started at 1 and they concluded 18, so that's going to be my upper limit. Looks like 4 is always present, so I want to keep that in my formula, but it looks like the exponent now should be the I. So again, take turns plugging in the integers 1 to 18 in that position as an exponent to see if you generate those terms. Let's look at D. Looks like the first term is 1, the second term is 2, the third term is 3. Okay, it looks like I'm adding 50 terms. So I'm going to put a 50 up here. There's no exponentials like there were here, but that's okay. Let's just let the formula be I. because if I is 1, I generate 1. Next, I would have to be 2, and I get 2. Next, I is 3, I get this, until I conclude at 50, and I get 50 here. And the pattern with the plus, dot, 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 plus indicates that this is the pattern that continues, and this formula would generate those. All right, let's look at E. We've got some fractions, so we really want to focus on the numerators and the denominators and look for some structure and some patterns. This is my first term, this is my second term, my third term, fourth term, etc. And I noticed that these numbers 1, 2, 3, 4 match the denominators. So if I had to figure out what my upper limit was, I would say if this is the first term and its denominator is 1, then this is the last term. So it must be that I'm adding 15 fractions. All right, so in my formula, I'm going to create a fraction bar. So I noticed that in the denominator, I'm going to put my I, because I advanced through the integers 1 through 15. Now look at the pattern with the numerators. 2 compares to 1, 3 compares to 2, 4 to 3, 5 to 4, 16 to 15. Looks like I'm always adding 1 to I to generate the numerator. And the last sum that we want to rewrite as summation notation. So remember, this is term 1, term 2, term 3, term 4. And this is your nth term. First term, second term, third term, fourth term. Okay, I got to figure out how many terms I'm adding, but the thing is that I don't have a finite number here. I just have an n here. I want you to think of this 1 as being 1 over 1. Let's make 1 a fraction by putting 1 over 1. 2 and then 4. I'm always doubling. I'm looking at patterns for the denominator. I multiply this 1 by 2 to get 2. I multiply this 2 by 2 to get 4. 4 by 2 gives me 8. So it looks like I'm always doubling. It's a little bit hard. So let's look at something else. So 2 is actually equal to 2 to the first. I'm thinking of powers because I see that down here in the nth term. 4 could be rewritten as the power 2 squared. 8 is 2 cubed. I think I see the pattern. So 1, this denominator right here is 2 to the 0. So I'm thinking that the upper limit is actually going to be, if this is term 1, the upper limit is going to be 1 less than this number right here. So I'll come over here, 1 less than n. So I'm thinking my upper limit, let me see, is that right? Is that what I want to think that I want to stop at? No. I want to stop at actually just n. Let's try that. Sometimes I have to like try something and then generate to see if I'm correct. Okay, so I'm going to create a fraction here, and actually this fraction right here is going to be this expression, 1 over 2 to the, and instead of n, let's let that be I, and then I have minus 1 with the exponent. So let me just try this real quick. If I is 1, then 1 goes here. I would subtract first and get 0. 2 to the 0 is 1, so I'd have 1 over 1, which generates that first term. Let me try I being 2. If I is 2, I have to subtract 2 minus 1 and get 1. So I have 1 on top, and I have 2 to the first, which is 2. I'm going to try one more. If n is 3, then I'm going to subtract here and get 2. So that would be 2 squared, which is 4, and I still have the 1 on top. So that is the third term. Going to the last term, if I is n, I would plug in n here, and that would generate exactly that nth term. Sometimes they're not easy, and you just kind of have to like guess and check. Guess what you think it is, generate a few, and then tweak it from there. All right, that's summation notation.